Hello everyone, in this video we're going to talk about Geometry Reader and we're going to continue with the implementation of Apple Watch layout. We're going to see how we can create those animations when icons are far from the center. And we are going to remember a couple of math classes from the school. Let's get started. My name is Pete and this is SwiftUI Tips. In UIKit, you need to explicitly say how views will adapt and constrain related to other objects in the screen. In SwiftUI, all of that is automatically. It's just magic. For example, look at these view colors in a Z-stack. The only thing I did was drawing the views there and adding some padding. SwiftUI did the rest to setting up constraints and space for each of them. This is super cool, right? But what will happen if this is not what we want? What if I want, for example, a custom padding? In this case, we have a hard-coded value. But what if I want just a width related to the size of this color blue? Or, regardless of the device screen, how to add a frame with the half of width and height for this view? How can I do that? All of that is possible with Geometry Reader. Geometry Reader is a container view that provides information about its size and coordinates. If you need to push a view out of its default boundaries, keep equality between view size, or generate animation based on view's position, Geometry Reader is the way to go. Geometry Reader provides a parameter within its view builder closure, a geometry proxy object that gives access to the actual size and coordinates of the container view. As you saw in the example, we are using proxy.size to establish a custom padding and frame size, and not hard-coded values. This is cool. In this way, we can use the same code for multiple screen sizes, and the proportions will be equivalent for larger screens. For example, iPad. But there is more. There is a great method called frame from Geometry Proxy that provides access to local and global coordinates for your objects. Let's see how that works. Local coordinates are related to the container of parent view, while global ones make reference to the whole screen. Let's see that in action. I set up the Geometry Reader container with gray color to explain this better. Min x and min y from local coordinates will always be 0, which makes sense. Locally speaking, that will always be the starting point for each view. Min coordinates represent the top left corner of the view. Take a look at max coordinates now. This time they are larger, 300 to be more specific. That also makes sense, since the container has a frame of 300 for width and height, and the bottom right corner represents this position. Also, look that size width is 302, which is right. But look at the global coordinates. They are pretty different from local ones. This is because they represent the exact location in the screen for min and max coordinates. These coordinates will be affected by any padding or offset you add to the view or its parent. This is a great tool to make UI with awesome custom layouts. Now that we know the basics for Geometry Reader, let's continue with our Apple Watch layout implementation. Let's see how can we use Geometry Reader to produce that scaling effect when icons are far away from the center. Okay, let's continue from what we left in the previous episode. The lazy grid and offset for even rows are set. Now, let's compare this implementation versus Apple Watch home screen. It turns out that icons disappear when they are far from the screen, but what is actually happening is that those icons in the edges have a small scale effect compared to the ones closer to the center. In SwiftUI, there is a modifier called scale effect, which produces this change in the size of a view. Let's check it out. Now the icons have the half of the size they had before. Okay, adding the scale effect looks really simple. The problem is to calculate that scale value. It will depend on the position of the icon versus the center of the screen. Let me show you what was my approach using my blackboard. This is science, my friends. Okay, seriously, what is the problem? Here we have an iPhone and a green axis that will help to represent the problem. The red dot represents the center of the screen, and as closer to the center, as larger will be the scale value. Now the question is, how we calculate this value? We have this blue point that represents the coordinates of an icon in the grid. We need to calculate this blue line that represents the distance between the center to the icon. Now more questions. How to do that? Well, if you remember your math classes in the school, there is a formula to calculate the hypotenuse of a triangle, the famous theorem of Pythagoras. Why is this important? That's because we actually have a triangle problem here. That makes sense. Then, how we are going to calculate A and B? It's simple calculating the x and y distances and get its absolute value. Let's jump to the code and build this function. Very nice. Okay, we have the function to get the distance between points. Now what? Here is the tricky part. We need to also calculate the distance between the center and the edge of the screen. But this point in the edge needs to be part of the same line that is covering the icon. I faced a lot of issues figuring out how to find this point until I realized two things. The first one is that we have one edge coordinate already. For example, here we know that x is 0 because we are in the left edge. We can conclude the same for other edges too, 0 or max value for x and y, respectively. Pretty nice. Now we have to find only the missing coordinate in the edge. How can we do that? Maths to the rescue again. This is the second thing I realized, the equation of a line. This equation is the rule to identify if a point is located in the line or not. X and Y represent the coordinates. That's easy. What about the other two? M represent the slope or the inclination of a line. For example, if M is 0, then we will get an horizontal line. For the case of B, this is a constant to increase or decrease the value of y. In this demo, we don't care about b, so we can discard it. Now, we can expand this equation even further. If we want to check if 2 points satisfy the equation, in other words, both being part of the same line, we can calculate the distance values between y's and x, as we did before in the hypotenuse. And with some basic algebra, we can get the formula to calculate the slope. Someone at this point might say, hold on Pete, why we want to calculate the slope of a line? That's because this formula is not only to find the slope, but also we can calculate a missing coordinate, which is what we want for the edge. And the cool fact here is that slope is the same for the whole equation. That means if we already have 2 points, one from the center and other from the icon, we can easily get the slope and then look for that missing coordinate, just replacing m with the previous slope value, and that's all. Magic, right? Let's jump to the code and create a function to calculate the slope. As you can see, this operation is really simple. We are just defining 2 CGM points and following the previous formula. Voila, the slope of a line. Let's actually start implementing this scale effect and see if everything is working. Let's wrap image in a geometry reader. If we're trying to run this right now with this geometry reader, we will get this. This is happening because now geometry reader is the container, and by default, it's trying to adapt as less space as possible. We need to move the frame from image to geometry reader container. Very nice, it returned to normal. Now let's create a scale function. We will pass two parameters, the geometry proxy that will contain sizes and coordinates, and the value from for each. We need to identify again the row number. That's why value is required. Not just that, we also need to consider the X offset in case it was applied. And to calculate the icon's position, we will use the global coordinates representing the center of an icon. For Y, it's just using directly mid-Y. Now we need to calculate the max distance to center, in other words, from edge to the center. We will create another function and pass X and Y as parameters. Here we are going to calculate the slope of the line using the X and Y coordinates and the center. But how are we going to calculate the center? Let's create a computer property for the center, and I will explain you why. Believe it or not, there's no other way in SwiftUI to get the center of the screen. We have to get the half of width and height for this. And it will be a computer property and not a store one, because we need to consider the rotation of the screen. Yeah, our divisors are not perfect squares, and width in portrait is different than landscape. Also, we don't know when the user will rotate the screen. That's why we need to be prepared to recalculate the center every time that happens. Move back to the previous method. Now let's calculate the slope. Let's go back to the blackboard one more time. We already got the slope. Now we need to do some algebra to calculate missing x and y. Let's consider that x2 and y2 are the edge coordinates. So the million-dollar question, when we need to calculate x or y? Well, that will depend, of course, of how large is the slope. A larger value means the line is closer to a vertical line, and a lower to an horizontal one. In other words, we need to consider the angle from the line related to the x-axis. But someone could say, oh, but that's simple, because if it's the corner, then the angle is 45, right? To be honest, I thought the same. Let's consider that condition of 45 degrees to calculate one coordinate or the other, and see if this theory is correct. Hold on. How to calculate the angle? More maths, my friends. This is the angle we want to identify. It turns out that slope is equal to tangent of the angle. Oh boy, this is scaling. Now we are dealing with trigonometry. We already have the slope, so with more algebra again, we could use the slope to get the angle applying inverse tangent. Are you still here? Cool. Then let's jump to the code and create a function to calculate the angle. By the way, how to get inverse tangent in Swift? We have to use a tan function. There you go. But this value is in radians. I don't want to overcomplicate things even more, but the result of this operation is in a range from 0 to pi divided by 2. If you actually want to get the degrees from 0 to 90, then we need to add this to produce that degree number. Here's another thing, we don't care about the sign. The angle will be the same to get the missing coordinate in the edge, no matter if we are in the left or right side. Let's use then the absolute value for the angle. Cool, finally the angle function is ready. Let's go back to calculate the distance between edge and center. Let's add a method to calculate the current angle from the slope. Now, we need to check when to calculate x or y. We decided to use 45 degrees for this condition. If we are above 45, that means we need to calculate x, otherwise is y the missing guy. First, let's get the known edge coordinate. What I'm calculating here is just checking if we are in the center of the screen. If we just pass the center down, that means we need to set y to the total value of the screen, in this case the total height. It's the same for x edge. If we are in the other side of the center, then we need to assign the whole width of the screen, otherwise it's 0. Now let's add the previous formula to calculate missing x and y using slope. You might notice this guy here and say, oh man, if m is 0, that will crash the app. Yes, that's true, but we'll never reach that condition because the angle needs to be 0 and we are only calculating this above 45 degrees. So don't worry. Finally, let's convert these conditions to CG points and return distance between points that we created earlier. Wow, this was a lot to consider. Let's go back to scale function and finish it. Let's add max distance to center variable. Now let's calculate the distance from current point to center. Cool, we are almost done. Now let's calculate the delta from the max distance versus the actual distance. Finally, we need to calculate the scale value just dividing the delta between the max distance. That's all, I guess. Let's finally run the code with everything set. Something is weird. If you notice, some icons are popping and drastically changing its scale value. But this is hard to debug with 1000 icons. Let's reduce the size to just 43 and also the columns to 7. Now take a look at Facebook icon. It's jumping. Definitely, it's something related to the angle we decided to use. For our debugging, let's add an axis to guide us and print the actual angle for an icon. Yeah, with Path you can draw lines in the screen, and thanks to Geometry Reader again, we can precisely decide the location of each of them. Pretty nice. Cool, this is super useful. Now let's print the angle. Let's pass value to get distance from edge to center function. That's right, it's jumping at 45 degrees. But then, what is the right angle to identify the corner? Manually, we can see that using iPad in landscape, it's actually closer to 35. That makes sense because, again, this is not a perfect square. The inclination is different. Let's replace the angle to 35 then. This is nice. Looked like that was a solution. But what will happen if I rotate the screen? Uh-oh. We got the same issue again. We're going to figure out manually that in this case the angle to compare is 55. But if we hardcode that, what will happen for iPhones, Mac, or future Apple products? That's not scalable at all. Did you get it? Scalable, scale values. I'm sorry, let's go back. This is a challenge for you. Pause the video for a moment and try to figure out how to calculate that angle. Don't worry, I will be here until you're back and give you my approach if you're stuck in this implementation.
A few moments later.
Let's jump to Blackboard one more time. Since that we don't care about the sign of the angle, we can concentrate in the first quadrant. What is the coordinate of the edge? Simple, 0, 0. So we have the corner, we have the center. Let's calculate the slope of that line. Now it's as simple as calculating that angle with the angle function. That's actually the device corner angle that we need to check in our condition. Nice, this now works in portrait and landscape. Finally, let's fix the scale a little bit more to get a closer Apple Watch layout. Instead of just applying the max scale to the object in the center, let's add a threshold or 70%. In other words, only objects closer to the edges will get a minor scale value. If the actual delta is larger than the threshold, then we will get the threshold. And to fix the scaling for the normal icons, let's add a scaling factor of 3.3. I found this value just with trial and error, but you can play with it. Don't forget to remove the axes we use for debugging and restore the numbers of columns and elements. Are you ready to see the final result? Wow. I love it. What about iPhone? Very nice. This app deserves to be executed in a real device. Give me 1 second. It's not cool? I know there is always room for improvement, but to be honest, I'm really proud of this result. Finally, the first time in my life that maths are useful. I really would like to know your comments about this experiment. Do you think there is a better way to do it? Please leave it down below. And don't forget we have more content for you here in SwiftUI Tips. For example, this playlist about UIKit in SwiftUI. That's all for me, guys. Thank you so much for following me on this journey. Have a great day.